Good morning, everyone. Welcome to operational aspects of SDN session. My name is János Mácsi. I will chair this session. I will have some announcements for you that probably you have already heard from class in the previous session. The posters are displayed in the exhibition area. You can look at them, and the poster authors are at the afternoon coffee break will be there, and you can talk to them. Demonstration is also scheduled the whole day during the coffee breaks and the lunch breaks. Please check the schedule on the online website. There will be extra events, booths and workshops in the evenings, so you can join to these extra events if you wish. And please fill out the feedback form. You can do it via the website or online, the Conf for Me application. And the last announcement about the gala dinner. If you want to have extra tickets, you can have at the registration desk. And the shuttle buses for the gala dinner will be is announced this morning for all the participants because the schedule is slightly complicated. I don't want to go in the details. Our first presenter will be Kireti Kompela. Just a moment. He's graduated IIT Kanpur. He holds PhD in computer science from University of South California, Los Angeles. Well-known personality at IETF, authoring and coding several different routing protocols. He's co-authored or authored more than 30 different RFC standards. He is the Chief Technology Officer for the Juniper Development and Innovation team.
Thank you.
Your floor is yours.
Thank you. So it's a mixed thing whether you want to be the first speaker after coffee or the last speaker before lunch. I think I prefer this. The other thing is jet lag hit last night, so I have too much nervous energy. I have too many slides. I probably finished them with 20 minutes to spare, but I'll actually try to go through them a little more meaningfully. So I want to talk about SDN, and I know it's a buzzword. A lot of people talk about SDN nowadays. So I'm going to give you 3 aspects of SDN and a small reminder, and then try to talk about the aspect of SDN that I care about, which is the abstraction. So I'm going to talk about SDN for programmability, and I'll define what I mean by that. I'll talk about automation very, very briefly, but some people think about SDN as automation. And then I'll talk about SDN for abstraction. So the first one I call SDN as a network OS, and the last one I call SDN as a compiler, and I'll tell you what I mean by that. So programmability is about, I have an operating system that I like, and that operating system will give me some base levels of APIs. It'll also give me some apps, but usually the apps that are there, they're good, but they're not completely sufficient for me, so I want some more apps on top of that. So I can go to another vendor and say, give me apps on top of this OS, or I can write my own. So programmability is typically about being able to write your own apps. So you want to improve performance, you want to improve scale, or you want to come up with a new feature. And so, or sometimes you just want to play. So, so you get this API, and you use that API to do all these new things. So that was the first sort of view of SDN, at least the one that the ONF, the Open Networking Foundation, came up with, which is I want to separate the control plane and data plane, call that my network OS. So similar to an OS on a box, on a server, or on your laptop, I have a network OS, I write applications on top of that, and I transform network states from a current state to a desired state, and that's what SDN is. So that was the definition of SDN by this, so software-defined networking. Automation is typically about, I know what I want to do, I do it at small scale. I prove it on one device, I prove it on 5 devices, I get the idea of what I want to do. Now I want a framework in which I can automate this for hundreds or thousands of devices, or in some cases, tens of thousands, like in a data center, in a cloud data center. So what you need to do is to parameterize what you just did on your 1 and 5 devices. You need to try to anticipate situations that you didn't find in your 5 devices, but what you might find in the real network or in the real data center. And then you need policies or rules to handle exceptions. And then you can say, okay, now I have an automation to do whatever I was doing. Typically configuration, sometimes reacting to situations. So again, the rest is up to you. So you have this framework, you have some tools, and so you've heard of Puppet and Chef. I was going to have to be careful how I say these things. And you build your automation from there. Some people think of this as SDN. I'm not going to go further into that. And the last one is you have abstraction. You have a low-level language, which is what's on your devices. So the machine language for x86, the machine language for MIPS. And then you have these higher-level languages that abstract away a lot of the details of the machine, allow you to express yourself in better ways. Many cases, imperative languages that say, do this, do this, do this. If you see this, do this, else do this, loops, whatever. Very prescriptive, and sometimes declarative languages, like Haskell or functional languages, where you say what you want, not how to do it. And then you say, okay, for my particular, what I want to have happen, this is how I'm going to express myself. And I will have a compiler that translates from my high-level specification, whether it's imperative or declarative, down to a lower level, what the machine understands. So I'm going to give you a quick picture of what that looks like. You have an SDN system. You have your requirements that you specify in this high-level declarative statement. And then you essentially compile them down to what the devices will accept. So this is what I consider SDN as a compiler. And the basic idea here is abstraction. So we have these 3 paradigms. You can have programmability, you can have automation, you can have abstraction. So this is not a value judgment. You have programmability, it's not the same as automation, which is not the same as abstraction. There are definitely overlaps among these. So for example, when you're doing abstraction, you're saying what you want to do. In a sense, you're building something new. And so in a sense, you're programming. But typically, the programmability is for features that you don't have, whereas the abstraction is for features that you have, but you want to manage in a higher level way, or you want to take existing features and combine them in a new way. So if you keep these kind of different, you say, okay, there are these 3 aspects of SDN. I do, since we're in this group that talks about operational aspects of SDN, again, not a value judgment. It depends on what you're trying to do. Abstraction and automation are trying to improve your operational side. They're trying to make it easier to run your network. Programmability is an interesting one, especially for the R&D community. You want to play with the network. You want to do something different. But for the operator, for the one who's running the network, having all these really clever guys going around changing the data plane, changing the control plane, and then saying, go ahead, please manage this, is an operational challenge. So from an operational point of view, automation and abstraction may be the aspects of SDN that you care about. From a research point of view, programmability might be what you care about. The last thing I want to remind people that we used to have, everything was software defined. Routing, switching, people built custom ASICs for it. But routing, I mentioned Cisco here, but someone reminded me that IBM did the same on a RISC RS6000. They turned it into a router. And it was a general purpose computer. And everything was software. The control plane is software, the data plane is software. So whether it's Cisco, whether it's IBM, this was all software defined. So we kind of tend to forget that and say, oh, this is this new thing we came up with in the last 3 years. There's actually, for some of us, older people like me, a delicious irony in this whole term, software-defined networking. So that gives me liberty to interpret SDN any way I want, so I'm going to use the abstraction model. How did we get here? People think of SDN as a separation of control plane and data plane. Again, from an operational point of view, yes, that's important, that's nice. I hate putting academic out there and having you guys throw something at me, but that's what does happen. From people who actually run the network, they say, hey, there's a really important part you've forgotten, which is the configuration, which is the management aspect of devices. So the actuality of a router is the control plane and data plane. Control plane is interoperable. Yes, there are problems, but mostly it's interoperable. The data plane is interoperable. It's the configuration that's so different from one router to another, even from one OS to another, one version to another. So how do we deal with this? And for me, that's where I want to take SDN. So instead of trying to separate control plane and data plane, what I want to separate is the configuration, call that orchestration because it's a nice new buzzword that everyone likes. And the goal is to have service agility, to be able to create new services from existing services, not to create new services like from programmability point of view, and to be able to do this much easier. So freedom from physics, that idea is from virtualization. So if you think about compute virtualization, you really say, I don't want to be limited by what a box can do and picking up a box and putting it somewhere else, all those physical attributes that make my life difficult. So I think we can have similar concepts in network virtualization. So you have these APIs. So what's new about this? We want to be able to define, so I said configuration is not standardized. So we want to make them high-level, standardized, and modular, so I can click things together much more easily. And so I would encourage you guys to look at OpenConfig, openconfig.net, where there are a number of operators, Google, BT, and a few others, who are saying, I want to create a standardized way of configuring BGP, of configuring MPLS. I will use the lowest common denominator. I want to write these all in Yang. So this is what the goal here is. OpenConfig, the start, I would like to see them do things more abstractly, but that's where they're going. And then you transform these high-level sort of device-independent things to device-specific data models, and that's basically what we want to do. So what this whole system really looks like in more detail is I have the service requirements and the declarative statements, and somewhere here there is, well. So you can see here that these databases that are here, you have service configuration database, you have a network telemetry database, and you have a device database. And what you're going to do is take this high-level service requirements, use the telemetry to say, how do I do this? Where do I put these services? Placement is a very important part of this. The analogy that you should have in your mind is compute virtualization. So if you go to Amazon, AWS, or if you go to your own private cloud and say, I want to run a new app, you don't get to say, I want it on this server. You don't get to say, this is the server specifications that I want. You get to say, I want 4 cores or 4 virtual CPUs. I want 8 gig of memory, a terabyte of data storage, and maybe 10 gig of network connectivity. And having said all this, the orchestrator, the computer orchestrator, will place your app on one of these devices, on one of the servers. So here you want to do a similar thing. You want to take the service requirements, take the network telemetry, and place the service on one of these devices, or a couple of these devices. I'm going to skip this slide. The idea is that SDN doesn't only apply at the edge of the network, it applies in the access, in the core, NFV, for those of you who are fans of NFV. But I want to get to abstraction. And the important thing about abstraction, today we spend a lot of time focused on the device. We want to say, this customer is connected to this port on this VLAN to this physical device, and this is the service that they're going to get. And placement is a very important part of that. And what I want to do with abstraction is to say, let me take away some of those details. Can I now specify the service in a slightly more abstract way? Can I remove some of those details and let a computer actually fill in those details? So I'm going to give you one example. There are two here. You can study the others at your leisure, or you can completely ignore them. It's up to you. But I'm going to take a service data model, which is a VPN or closed user group, whatever you want to call it, and say, how do I think of this in a more abstract way? So if you don't know VRFs, this might, or eVPNs, or whatever your favorite VPN is, this might not resonate as much. But if you think about your favorite type of virtual private network and how you would configure that on a Juniper or a Cisco or whatever your favorite device is, you specify a lot of things that maybe you shouldn't have to. So for example, for the closed user group, I want to say, I need to tell the network, where are my endpoints? Which one is my customer, and where do they come into the network? And I need to say things like, is this an IP VPN? Is this an Ethernet VPN? What's the topology? Is it any-to-any? Is it hub and spoke? What is the connection bandwidth? But I don't want to give too much more than that. I don't want to say, what is the technology? So for example, I'm going to use the example of an Ethernet any-to-any VPN. I could do that as a VLAN. I could do that as a VPLS. I could do that as something new, relatively new, called an eVPN. Do I, as an operator, want to say those details? Yes, I do, because I'm a geek, but I shouldn't want to. I mean, the problem is, and this is why I think we are where we are with networking, we love playing with these knobs. We love specifying too many details. We need to say, step away. Somebody wants Ethernet connectivity, that's what I'm going to give them. And whether that particular customer or that particular entity gets a VLAN or an eVPN should depend on other things, and let the computer figure it out. So I definitely don't want OS-specific details. So if I were to take that particular example, I have a template, which is what my service looks like. And I want to put in details like, this is for BFA, which I will leave unexpanded. I'll say that the endpoints are ABCD in my network. This is an Ethernet VPN, and the topology is any-to-any. And I might also say, I should get multicast with this, or this is upfront. So I should get multicast with this, or this only unicast. And then I say, okay, the connection is essentially everyone gets 1 gig, except the headquarters gets 100 gig. But notice that there's no mention of whether this is running over, plain Ethernet. Is it running over MPLS? Is it using BGP or LDP for signaling? All those details. And I don't even tell you which PEs, the provider edge routers, this connects to. This is the job of the orchestration. This is the job of the thing that says, I'm going to take your requirements and then say, knowing that this router is very busy and this one has lots of capacity or lots of fib space, I'm going to place that customer. So assume that assume that A can connect to 3 different devices. Which one do I use for this particular VPN? Well, let the computer figure it out. That's the point of this whole thing. So then I get down to the next level, which is when I compile it down to a physical device. So I'm going to say I'm going to use MPLS, I'm going to use BGP for signaling. The technology that I'm going to use is actually EVPN, not a VLAN. I'm going to have to actually put down some route targets for this because this is BGP based. The connection, I've already said what it is, but I'm going to pick PE1, PE3, PE4 in my network, and the physical interfaces, probably also the VLANs. And so now I'm getting down to more and more level of details. But from my point of view, as an operator, I should only have to specify what I did when I said, this is my customer, and these are the endpoints. So essentially what you have is, you specify a certain level of detail, and then the computer, the program, the whatever you want to call it, the orchestrator, the SDN system, using telemetry, using the current state of the network, says this is where your service goes. And that's, for me, what SDN is. It's the ability, it's the analogy of compute virtualization for networks. It's the ability to specify what you want in a higher way and allow a computer to join the dots. I give another example, which is more about LSPs, infrastructure. I'll skip that. I don't know how I'm doing on time. But I want to come back to this thing. There probably are many, many different ways of expressing data models. The one that Juniper used for a long time was basically XML stanzas. We had our internal schema. And what the industry is moving to is specifying the data model structure in Yang, and then specifying, so that's more like your template. And then when you fill in the details for a particular service, you again use XML. So XML has a lot of nice properties. Like I said, the OpenConfig guys are using XML. About 2 years ago, nobody knew what XML is. Today, there's 200 XML models, not XML, sorry, Yang. So nobody knew what Yang was. Today, there are 200 or more drafts in the IETF with Yang models for everything, including probably, never mind. So that's the language that I think we should go for. It is typically for describing configuration that lives on the device, but I think you can use the same thing for expressing services in a more abstract way. So I mentioned telemetry. I'll come back to this just briefly, that telemetry is a very important part of all this. And the thing that, as you say, I'm going to let a computer do more and more of this, I think you also need to give the computer more information to be able to make intelligent decisions. So everyone thinks about, a pilot flies a plane. Well, pilots don't fly planes. Especially commercial jets are flown by computers. And the reason they're flown by computers is they're measuring all kinds of things like microcurrents, temperature, pressure, all kinds of things, and optimizing how the plane flies at a speed and at a granularity that humans cannot do. And I think the same thing applies here. If I want to optimize a service, and in fact, not just place a service the first time, but move a service from one place to another. This is something we typically don't do. So if I give you an Ethernet VPN, you're stuck on this particular box, you're going to stay there until I have actually a special event to move you from here to there. And, but if you look at a VM, a virtual machine, your app is going to run on this server, and then because of telemetry, that server is too busy or something's happening, your app will be picked up and moved somewhere else. And you don't actually know that that's happening. We should be able to get to that kind of agility in the network. And so we need information for that. We need telemetry. So in talking about all of this, we have to interact with the SDN system. And so I'm going to go over that very, very briefly. You talk about programmable networks, but here I'm talking about an API where I give you the service requirements. I'm going to specify them in Yang. I'm going to give them to you in XML. But I'm going to give them to you in this abstract way. And you're going to then have to, you being the SDN system, place this, and so on. So how do I interact with the SDN system? I have this API, typically netconf or restconf, which is how I'm going to transfer my service requirements to you. I also have an API from the SDN system going down to the box, again, netconf or restconf, telling the box the details that I want. The difference between the two is the API above, what people sometimes call the northbound, is higher level, more abstract, less details. And the API below is everything the box needs to actually implement the service. So we use data models for this. And the important thing here is that APIs are very language specific, very syntax oriented. Data models are really capturing the essence of what you want. So you can derive the APIs in C and Java and Ruby and Python, whatever your favorite language is, from the data model. And this is actually a very powerful paradigm. The other thing that we don't have enough information about today, we don't have enough research into, is between SDN systems, how do I interact? So for example, the SDN system on the right could be my VPN, and the SDN system on the left could be doing the infrastructure planning, and the one on the right needs the one on the left to know whether I have enough core bandwidth to satisfy my VPN requirements. So that's for further study. So to conclude, I want to say that essentially what the view of SDN that I have is you want to get away from the boxes. You want to think in a more abstract way. You want to separate service configuration from the devices, not control plane from the data plane, but the service provisioning from the control and data plane. You want to specify this abstractly in a device-independent way, in an OS-independent way. You want to use telemetry to optimize service placement, not just the first time, but maybe every day, every week. You want to move services around. You want to compile these abstract specifications to device-specific models. In all of this, you're using data models. And you want to monitor these services continuously. So if you look at all of this, this is exactly what operations is about. I want to specify a service, I want to place a service, I want to monitor the service, and I want to move services around to improve them. How you interact with them? Well, you use data models. You use data models at a high level. You use telemetry to feed this with the right information to make decisions. We have to still figure out how SDN systems interact with each other, whether they're cooperating SDN systems or hierarchical SDN systems, and we have to standardize these models. So today, like I said, OpenConfig is doing the first step here. They really care about BGP and MPLS configuration. At some point, we want to talk about how do you configure services, and so we want to take what they're doing much, much further. Questions?
Yes. Any questions from the audience? If not, probably I have one. You mentioned declarative languages.
Yes.
And you listed Yang as an example for that can be somehow used. Do you think that Yang can fulfill all the requirements of data sender, service provider, access networks? Is it possible with Yang or
So, to be very frank with you, I think it is, but I don't have proof, a wide enough proof. I think the big part about Yang is today we use Yang for device-specific models. And so the important part, as you said, the declarative part is, can I remove these details and specify enough that I can tell the network what I want without specifying all the other details? So I think one thing is, can Yang be used in a more abstract way than it is today? The second is, can it be used in all these environments? And I think the answer is yes, but we have to prove it.
One comment though. is that, yeah, you can abstract how much you want, but some of these technologies are not inter-exchangeable, right?
Yes.
Some of them provide some features and some of them provide other features, right? So
right.
you would still have to be able to put details there.
Yes, and so there's two parts to that. There is the part where you want to know, I decide that, so in the Ethernet example that I just gave you, I decide I want to do an EVPN, but this particular device may not be able to do EVPN. Maybe the only thing it can do is a VLAN. So I need capabilities coming back from the box. So the SDN system has to know what are the capabilities of all my boxes. So that's one. And then the other thing is, I need to know, and this is what telemetry will give you, more details about, maybe this can do EVPNs, but it's, has no more space in its fib, so what do I do there? But I think we have to say, okay, what are the details we need to give, and what are the details which we don't need to give? And this process of moving away from the box starts with us. We have to think about the network differently. And I think that's the biggest thing about SDN, is to say, stop thinking about the boxes, start thinking about the network and the service. And when we do that, we'll remove some information. Maybe we'll remove too much. And then, as you said, we come back and say, no, I need to put that back. So I think we have to play with this. We have to find the right level of abstraction.
Thank you very much for a very useful presentation. Our next presenter will be Giulio Ibarra, who holds a PhD and he's an Associate Vice President for Technological Augmented Research at Florida International University. Dr. Ibarra is responsible for strategic planning and development of advanced research networking services, including the development and management of AMPA's International Exchange Point for research and education networks. And he's principal investigator of America's Lighthouse AmLight, NSF International Research Networks Connection funded project, and he will present his presentation about this AmLight in the beginning.
There we go. Ready? Good morning.
Headset.
Okay, great. Good morning, everybody. My name is Julio Ibarra. I pronounced my name in Spanish correctly, so being in Lisbon, and in Porto, I want to make sure you hear my name as it's supposed to be pronounced. I want to, this presentation here will inform you of our experiences with the use of SDN in a project called AmLight. AmLight provides international and intercontinental research and education networking services. And this is a presentation based on the paper that's on the website. Authors are myself as principal investigator, Heidi Morgan as co-principal investigator, and Geronimo Becerra, chief network engineer for AmLight. Okay. So first, let me tell you a little bit about who we are with our project. Thank you. AmLight is a project at Florida International University. It is a project funded by the National Science Foundation through a program called the International Research Networks Connections Program. This program funds a number of projects for connecting the U.S. to different regions of the world. The AmLight project primarily focuses on U.S. to Latin America connectivity. There are projects that connect the U.S. to Europe and also to Asia. Our partners are in Latin America, the Academic Network of Sao Paulo, ASP, the National Research and Education Network of Brazil, RMP, the Regional Academic Network of Latin America, Red Clara, the NREN of Chile, Reuna, and also one of our science collaborators is the Association of Universities in Research and Astronomy, AURA. let me inform you a little bit about the resources involved with AmLight. The exchange points involved with this project, AmPath is an academic international exchange point in Miami, Florida. It interconnects Latin America and Caribbean research and education networks to other RENs throughout the world. The Southern Light International Exchange Point in Sao Paulo, Brazil, interconnects the Brazilian research and education networks and also to the Red Clara regional network of Latin America. And then AmLight provides the international links that connect the U.S. to Latin America. I'll talk a little bit more about the infrastructure involving AmLight. Let me also state that the AmLight project is for Latin America, so it also includes connectivity to Mexico with our collaborations and partners in California and Texas. This particular talk is going to focus, though, more on the connectivity to South America. Let's see. Okay. Let me tell you a little bit about what the AmLight topology looks like today. We're currently operating a set of 4 10 gigabit links that's based on 2 topologies. One is our SDN layer 2 ring. This ring connects Miami, Sao Paulo, Santiago, Chile, and back to Miami. In the logical diagram that you see here, it is the red ring in the center, the green ring in the center. The other topology is based on MPLS, a layer 3 ring, connecting Miami, Fortaleza, Rio de Janeiro, Sao Paulo, and then back to Miami, and that's represented in the yellow. I also included a physical map in the upper right corner. Those links there are representative of the operators of the submarine cable systems. We currently are using 2 operators, and they provide the physical diversity that we need for this project, that we use for the redundancy services that are part of the AmLight network. In August of this year, we're scheduled to add a 100 gigabit link between Miami and Sao Paulo, and I'll briefly mention that link will be used for experimentation and then evolve into production services for our project for AmLight. We have a number of let me tell you a little bit about the connections that the organizations that we're supporting. There are 13 different research and education networks that use this infrastructure, and through their connections into the campuses, there are over 1,000 universities and research centers throughout Latin America that are served by these links. So it is a very important facility that is currently in operation, and so I want to share with you a little bit about our experiences with SDN with this network. So before I get into what we actually did with SDN, let me tell you a little bit before how the network was being operated before SDN. So with the coordination or the configuration of circuits on layer 2 circuits, this work was mostly done manually with static VLANs. There was a high degree of coordination involved. It involved a lot of different teams involved with the different networks that the circuit was provisioned on. We used the per VLAN RSTP protocol. We had this capability because on the SDN ring, or the ring that would support SDN, was using brocade technology. And so this was a feature that we had to use, but this, later on, we realized presented some interoperability issues with our other partners, their network, because not all of them use brocade. So that became a challenge for us. This constrained some of the redundancy capabilities that we would be able to implement with our network operators. The redundancy on these two rings that I showed you in the previous slide, one methodology we used was based on Q&Q. The other one was based on layer 2 VPNs. To be able to do this interoperability and set up the redundancy, we had to use some additional ports to implement the redundancy across these rings. We were successful in achieving this, and the infrastructure was operating quite well. So in terms of operations, the reasons for moving to SDN were to be able to, and I'm going to talk to you a little bit about this right now in the next slide, but it was to really improve our capability to provide better services to our users, not because the network was lacking on any functionality. Now, the two key motivations for moving towards SDN was improving operations efficiency and introducing network programmability. And let me tell talk a little bit about each one of these now. So, in motivation, the first motivation with improving operations efficiency, we were observing that requests for layer 2 circuits were increasing. The provisioning process was becoming more complex. With this infrastructure, we were setting up temporary circuits for demonstrations, also permanent circuits for different types of projects. So the complexity was increasing as the infrastructure developed. This required quite a bit of coordination with all of our collaborators. And the amount of time and effort that the network engineers were spending was getting to be rather significant. We measured this based on the number of phone calls, number of emails going back and forth. There was a lot of engagement of different network teams to provision these circuits. We also were involved in having to work with different technologies that different network operators were using as well. Not everybody was using Ethernet as their, or let's say, brocade technologies providing Ethernet. Some people were using SDH and provisioning Ethernet over SDH. Others were provisioning their circuits over routers based on MPLS. So there was a mix of technologies, and as you can imagine, and most of you realize, a number of you, we've worked with you on these projects, the troubleshooting can become quite complex in dealing with these kinds of situations. So we observed that some circuits took weeks, even months, to get provisioned. We've had cases where it involves multiple continents, South America, in the US, connections out to Europe. We had some connections out to Asia as well. So we really realized that something had to be done to improve this. The other reason for moving to SDN was to introduce network programmability into our environment. We really couldn't support applications that were interested in having more control of the network and being able to work in a more dynamic fashion. We really had little to no support for network-aware applications. We only were able to provide researchers with visibility on the status of the network using SNMP. So for novel applications, our capabilities were rather limited with the infrastructure as it was, just providing essentially transport to the different network users. So I'll talk to you now a little bit about the scenario that we ended up deploying. So we deployed OpenFlow 1.0, and we used the hybrid port features of the brocade switches that we had deployed in our network between Miami and São Paulo. This was a decision that we made given some of the limits that we had to work with OpenFlow 1.0. But there were some trade-offs in using this feature of brocade. To improve operations efficiency, We deployed Internet 2's OESS orchestrator. We use Oscars and the IDCP protocol for interdomain provisioning of the layer 2 circuits. And we also, later on, added OpenNSA and made available the NSI protocol, which is standard, and we encourage our network users to use NSI as much as possible. For programmability, we used Internet 2's flow space firewall. And flow space firewall provided a virtualization layer. It's a hypervisor that essentially allows the applications to spin off virtual networks. And I'll talk a little bit more about that. But this gave us our first introduction into introducing SDN into our links, and this was done last year, and it's been a good story. And with this slide here, I want to show you our architecture at AmLight using these technologies. So from the bottom up, if we look at the data plane that we have here, we have our switches. You see at the left, 2 switches that are deployed in Santiago, Chile, called Andes 1 and Andes 2. We have 2 switches deployed in Miami called AmPath 1 and AmPath 2, and the 5th switch in Sao Paulo, Brazil at Southern Light. And these switches now are managed through the virtualization layer provided by Flow Space Firewall. And we have our control plane integrated with that infrastructure. And I don't know if you can see clearly here, but these, if I can point with this. Anyway, the boxes above the virtualization layer, you see there are purple boxes labeled SDN IP ONOS fiber. These are test beds that are currently operating. And each of them have their own flow space. They have been allocated slices, and they're essentially contained within their address space using the infrastructure so that don't collide with each other, basically taking advantage of the virtualization capabilities provided by Flow Space Firewall. The boxes in yellow are actual applications that are running today and operating the AmLight infrastructure that provide transport to the networks connected to AmLight. So here we are using OESS to provision circuits, and those circuits connect to other networks in the US, such as Internet 2, connect to ESNet, and essentially have connectivity to other networks that are using these protocols as well. So we have Oscars for the interdomain capability and OpenNSA based on NSI. We have the ability of our demos now are using this infrastructure. And we have a new project that I'll talk briefly about later for developing a software-defined exchange infrastructure. So these are all implemented as test beds at this time. And we have the capability of supporting new test beds, essentially as the gentleman before me talked about. They can bring their own application and controllers, provide their own northbound API, and we can support that. And that's something that if you have interest in collaborating with our collaborators in Brazil, this capability is available today. So I'm going to transition now. We just talked about the deployment strategy and our architecture. I want to share with you some of the findings that we reported in the paper that you have available on the website for the conference. So there's a number of categories that we use here for measuring the results of this project. On the left side here we have our direct connectors in the AmLight project that are running these protocols. We have other networks that are also running IDCP or NSI, and then we measured other networks that are not running these protocols to see what the differences were before and after SDN was deployed. So one measure that we used was average time to provision a new circuit. The other one was average number of emails exchanged between network operators. Before SDN, we measured an average of about 5 days to provision a circuit directly to our connectors. Once the SDN services were activated using the orchestrator, OESS, it took less than 5 minutes to provision a circuit. In terms of number of emails back and forth with the different network teams, before SDN, on average, it was about 10. With SDN, now it's 0. With other networks that connect to our direct connected networks, before SDN, because you had now layers of networks connected and more engagement involved, it took an average of about 12 days to provision a circuit. Now it's still less than 5 minutes to do this. Number of emails exchanged was about 65 when you're dealing with layers of different networks. Now it's 0. So you could see that we have increased our operations efficiency in terms of provisioning quite dramatically with the use of SDN and OpenFlow. And the numbers just get worse as the networks extend further out, and especially if these protocols are not being used. So with, the numbers here that you see, or the columns that you see here with dashes, essentially are the same numbers as you see before SDN. No change in improvement. With introducing network programmability, we observed the categories here on the left here: network view, provisioning defined by the user, multipath experiments, and flow-controlled hop-by-hop. These are different categories that we use to measure the difference before and after network programmability was introduced. So with the use of without the use of SDN, essentially all we had to offer our users was SNMP for visibility and to have just some understanding of the state of the applications on the network. After SDN, we had now SNMP as well as OpenFlow available that applications can use. Provisioning defined by the user, that was not available at all before SDN. Multipath experiments, only static capabilities were available. Now with SDN, we have full OpenFlow access through a dedicated slice. Users are able to do whatever they would like to do within that slice. And the same thing with flow-controlled hop-by-hop. It was another. So the main point of this is with network programmability, this is what we have identified as a real step forward with our project. Now network-aware applications will be able to use this infrastructure to really experience some innovation capabilities and use AmLight as a platform for innovation. So just some lessons learned from this work. Some gotchas for us in working with legacy protocols and old switching line cards. They made our deployment more challenging. We had to work around this by dedicating additional ports to figure out ways of making these connections without impacting production. Out-of-band control plane services for OpenFlow. This was a challenge. We had to essentially use one of our partners' networks to provide IP transport between the exchange points so that we had out-of-band control between the controllers and the switches in the data plane. In the future, our plans are to explore and add new features, especially related to troubleshooting and security. As I mentioned, we are going to create a software-defined exchange. In the AmLight environment, we have quite a few different networks that have deployed OpenFlow, and so essentially they're OpenFlow islands that need to be connected. And with the SDX capability, we're looking at interconnecting these islands over this international infrastructure between the US and Brazil. And also in our roadmap is to migrate to OpenFlow 1.3. Some of the features in OpenFlow 1.3 will definitely improve some of the issues we discovered, like for example, network convergence time, the infrastructure when we've lost connectivity between a switch in the data plane with a controller. The network convergence time can be significant. OpenFlow 1.3 provides some functions to be able to improve that. I want to thank our sponsors, the National Science Foundation, our collaborators in Brazil that support AmLight, and also in Latin America. These are our award numbers for AmLight and a number of other projects. And our documentation is available at this website here, sdn.amlight.net. Our papers are there. You can find out more about our deployment experience with SDN on AmLight. Thank you very much.
Thank you very much, Julio. Any question from the audience? Yes.
That was a really big improvement. Well done. And your customers are happier.
Yes.
One question I have is, if we marry the two presentations, you could think about using OpenFlow southbound from your controller, and the interface that you give northbound to the NRANs to manage their networks could be based on something higher level rather than them programming flows and ACLs and stuff. And that might actually give you a better level of confidence that the customer is doing the right thing and not messing up some ACLs that somebody else might be using or something. And sort of try to marry the two. So, I mean, the fact that you're using OpenFlow down to the switches doesn't mean that you need to give OpenFlow up to the NRANs. And that's just a thought.
That's true. That's true. This is something that we can support. Today, we have the virtualization layer based on flow-space firewall. But essentially, a researcher or an operator could bring their own application, their own controller, and plug it into the environment, and essentially provide their own northbound API. So that capability is there today.
Diego?
Yes, the question is very much related to what Kiriti was asking. It's precisely about the security model you're following, how you identify and how you assign rights or permissions to the different participants in the AmLight project to deal with or to take access to the APIs. Were you using, which is the security model you're applying in the project?
Okay, so we primarily we provide slicing capability to allow the user to deploy their test bed and be able to work within that slice. So this is one way of providing isolation and security between the different test beds. Now, further up on the stack with that, that's something that we will certainly, we have a conversation with the user just to make sure that what they're doing is not going to impact our production environment. We also, I didn't show on this slide here, but we actually have a test environment that we would actually connect the user's controller and application, test it there first, make sure that it's not going to create a problem in the actual environment here. So we have the brocade technologies there. We have a number of other OpenFlow switches. We have the capability of testing the user's application before it could cause any kind of issues for us.
1 minute. So 2 questions. Yeah, sorry.
Yes.
So one thing, the operational aspects and the efficiency of that wouldn't really require you to use OpenFlow, right? So because you could just do that with netconf, really. You could just do an OpenNSA and then netconf control that, right? You don't need OpenFlow for that. So the reason you chose OpenFlow was that to give your customers more programmability of this, right? Or why? And really, what's the use cases?
We adopted OpenFlow because it's becoming more of a standard. And we have, in the networks that we connect to in Latin America, we had a number of test beds that were already using OpenFlow. And so this started to provide a common language in which we can configure the switches and isolate, create a controller that talks OpenFlow and gives us a way across all the different networks that we're using to be able to provision the layer 2 circuits in a much more effective way. So OpenFlow provided this. It could be something else.
I don't see it's more effective to do layer 2 circuits using OpenFlow, but I think that's a lot more hard. And as Kreti said in his presentation, it adds other problems in operations, right?
Well, I could say that from our point of view, it's simplified a lot of things. In terms of how we measured efficiency, it really simplified the whole process of deploying a layer 2 circuit across multiple networks, and the tools that have emerged are available with OpenFlow. So, for example, the Oscars protocol, the OpenNSA, the APIs talk OpenFlow, and so we basically use these capabilities that were available for the academic networks. Now, I'm not saying there's not other things, but for our particular community of users and the resources that were being developed, these were available for us to deploy and open source that we could make use of.
Okay, thank you very much. Thank you for the presentation again.
Thank you.
Our next presenter will be Dale Finkelsom, who is working for Internet for more than 6 years now. Earlier, he was at the University of Nebraska. Currently, his research interest focused on international engineering and related activities. He will replace Eric Boyd, the Senior Director of Internet 2, in his presentation, because Eric couldn't make it this year. Perhaps this is not the beginning, I think, of your presentation.
Yeah, where's the... Excellent. Thank you. So what I'm going to do today, hopefully in about 20 minutes or so, is go over what the Internet 2 network looks like these days, because some of you may not be familiar with that. And then talk a little bit about some of the experiments and projects that we're developing using primarily virtualization tools with SDNs sitting underneath them. That was a mistake. That's 5. And which one? This one. Yeah, okay. All right, so this is what our current network infrastructure looks like. Each of those large red dots are AL2S nodes. They are either Brocade or Juniper switches. There are roughly 30, some of them out there at this point. There's been 2 or 3 that have been added since this diagram was done. They are interconnected at 100 gig. All of those gray lines are 100 gig connections that connect the switches together. There are still 10 routers that live in the network. They're not shown on this particular diagram, but the 10 routers each have dual 100 gig connections to the co-located switch in the city that they're at. And then we show a number of the various connectors and so forth that are currently having connections into AL2S. The software stack that we're employing at this time is a little bit more complex than the one that we used to do. There was a point in time when pretty much all that we did at Internet 2, more or less actually when I started, or prior to that, was live up here at layer 3. And basically we had a layer 3 network, people connected to it, and we gave them routes, and they gave us routes, and everybody moved traffic, and it was a reasonably happy environment. What we do now is we have multiple layers of services that we offer. We have our most fundamental service, which is a basic circuit or wavelength service. We have something on the order of 16,000 miles of fiber in the US that we have potentially an 88 wave system deployed on, optical system deployed on. And we're happy to make wavelengths available to organizations that are interested in coming in at that level. So you find a couple of organizations that have utilized that capability. Above that, we have the network virtualization service as implemented with FlowVisor, which Julio was talking about. And that's where primarily the rest of my talk is going to be focused around, is at that particular layer. Above that, one instance of it is AL2S, Advanced Layer 2 Services. And then on top of that, in turn, is Layer 3, and then there's some above the net kind of stuff that I'm not going to talk about today. So I don't know why Eric put a pie in here. I've never really understood why he put a pie in here, but actually I sort of do. You could think of this as being the original instance of Internet 2. So simple, unitary thing that everybody understood, everybody knew how to use, more or less anyway. What we're looking at trying to do now is break it up in a more interesting way and make it more capable of delivering, not just delivering advanced services, but letting people develop advanced services that live inside this infrastructure where we don't necessarily have to be in control or manage the service or even offer the service. We simply give them the resources to create the service. And each of those different slices represents an opportunity, perhaps, for some group or individual to create some tool, service, whatever it is they wish to call it, that provides them some capabilities. So basically we're looking to create a situation where we give control of a virtual piece of our national network to organizations to do with what they are interested in doing. I will talk a little bit about the fact that we aren't doing this at random. We do have a vetting process, and as you might imagine. But what we hope ultimately is that this approach to providing an infrastructure and providing a service to the community that we serve will allow them to prototype advanced applications a little more quickly, perhaps develop new services that we would not be able to do in our production environment, to give them a place where there is the possibility of doing experimentation and hopefully have them sufficiently firewalled off from our production network that experimentation isn't going to impact the production traffic that we have. Right now, in terms of the development of virtualization, there is basically 3 slices operating. OESS, which is basically the AL2S, the Advanced Layer 2 service that Internet 2 offers. That's our fundamental Layer 2 service that we also run all of our Layer 3 traffic over and so forth. Genie Site Manager, which is a service that the Genie operations folks run. And ONOS, which I will, you've heard a little bit about already, but I'll talk more about later on. So you saw a version of this actually from Julio as well. This is a somewhat different, although very similar approach. Basically, we have our switches. These are the brocades and junipers. There's 30, 40 of them, however many there are. They talk open flow to flow space firewall, okay? Flow space firewall, in turn, talks open flow up to a controller that lives inside one of those kind of application worlds. So right now we're using the Knox controller inside of OESS. There's another instance of it there that also uses Knox. ONOS uses some other, I'm not sure actually what controller they use, and so forth. And then there's an API that goes up to the actual interface to the user community. You'll see this is going to show up in a couple different places here. It's basically the same every time it does, but it just gives you a sense of where this hierarchy goes. And again, what we're really focused on is right here. So right now we are in production support of OpenFlow 1.0. We have 1.3 in testing, both in testing in flow space firewall and OESS. That testing is taking place in an ongoing way. I mean, it's sort of give and take between the vendors and our development community. We are experimenting with Brocade's 5.8b implementation of OpenFlow 1.3. That, I'm not sure if that's entirely accurate. There's been quite a lot of movement on some of the revision levels with Brocade, so I'm not sure if 5.8b is the correct one at this point. But the point remains that we're working with them on that, and we are continuing to work with Juniper on implementing the requirements of OpenFlow 1.3 on their boxes. As far as hypervisor support, right now it will do both layer 2 and layer 3 matching. We have vendor supports for those revisions of the Juniper code, and sometimes those things change pretty quickly, so don't take it as gospel that those numbers are exactly correct at this point, but they're probably pretty close. OESS 1.1.6 is the production version. It does have a layer 2 trace in it if you're interested in checking that out. One of the things, of course, that's always difficult in layer 2 networks is understanding what paths you're taking and how to discover paths for diagnostic purposes and so forth. So that could potentially be useful. And we are accepting third-party controllers, as I said. But as I also said, we aren't doing this sort of just because you show up on our doorstep with a controller. That would be a friendly thing to do, I suppose, in some instance, but our production people might not like it. Basically, if you want to get access to a slice of the Internet 2 network, you contact the NOC at internet2.edu, ask for and subsequently receive a questionnaire that we have developed that basically goes through, and I don't know, what all of the questions are at this point, but basically tries to determine if you've got a viable option that might work. We expect you to download Flow Space Firewall and work with it in your environment and test it, make sure that your application works against it correctly. I'm sure, for instance, Julio did this at great length with their stuff before they started doing the work that they've done with the virtualization tools. You submit your package to the NOC, and it's, it's always helpful to have documentation. I mean, your engineers almost certainly know very well how to run this, and I am 100% positive that they wrote it in such a way that it is completely obvious and transparent how that application works. But nonetheless, a little bit of documentation is useful to the NOC folks who will be testing it. Logging, being able to log, errors if they should by chance occur is also, of course, very useful. The Internet 2 NOC will test the controller against our test environment, and if everything vets out correctly, they'll deploy it and give you a slice, and off you go. So these are just basically the kind of things that that we're hoping to find from whoever is submitting it. The most important piece of all of this is the last one. You know, a little patience always goes a long way in these kind of activities, because it is something that's fairly new, and it's a way of approaching doing networking that is fairly new, and subsequently it's perhaps not always as well understood as we think it is. Just a few things that are probably important. You really do have to be able to run this stuff against a Brocade or a Juniper. That's what we have right now, and you know, you really need to test against those devices. Testing against vSwitch is probably, it's okay to, you know, for a whole lot of very good reasons, but it is not going to necessarily tell you if your stuff will work with our switches. So you really need to test against that environment. Your traffic will not be mixed with our production traffic in the same slice. So you have, when you get your slice, it is empty. There is nothing there. You have to be able to generate traffic if you're going to figure out what's happening. The Internet 2 NOC runs your controller. You do not run your controller in this test environment. That may change over time as comfort levels grow and so forth. But for the time being, that's the way that it's being operated. We are often asked how good our OpenFlow 1.3 support is. Taking a bit of history from Henry Ford, our OpenFlow 1.3 support is very good as long as it's OpenFlow 1.0. And for those of you not from Detroit, the reference is to the fact that you could buy a Model T in any color as long as it was black. So, you know, we haven't got unlimited servers either. If you need a whole lot of servers, you're probably going to have to figure out how to provide them for whatever purposes you might need them. We have a few, but not a lot. Moving along in 2015, we continue to work on this stuff. One of the goals for 2015 is to get NSI built into AL2S. Right now, it uses IDCP, and for a whole lot of reasons, that's probably not a very good idea any longer. It's on the roadmap. I don't know exactly when this is going to happen. There's testing going on, and people are getting comfortable with various levels of it, and we'll see where it goes. The ONOS deployment, actually many of you may have seen, there was a press release, I believe, earlier this week about the fact that that ONOS deployment has in fact occurred, and it is working, and I'll have a couple more slides later on to give a little more detail about that. Continue to work on 1.3, continue to support both of the OESS and flow space firewall tools, which are, by the way, open source. People are welcome to download them and use them to whatever degree they want. And as we get more opportunities to provide slices and deploy slices for people, we hope that you know, we sort of get better at it and be able to kind of enhance that process so it's a little quicker and a little simpler and so forth. We'll just skip over that. We've already seen that. The next couple things I want to talk about are just a couple of ways you might imagine using our environment to solve certain kinds of problems. So one problem that very frequently comes up, as Julio pointed out, getting circuits, for instance, across multi-domain environments can be something of a challenge. You know, I mean, personally, I don't mind emails, although by the time you get up to the 50 and 60 emails to get a single circuit built, it does get just a little bit frustrating on occasion. And any way that we can work to achieve the kind of goals that he was able to achieve of 0 emails is certainly desirable. So one of the things you could imagine doing is use virtualization to create a multi-domain layer 2 service. And I'll go through in some detail here exactly what I mean by that. But it would presumably span some combination of campuses, networks, exchange points, NRENs, whatever the scope of it might turn out to be. So what do you have to do? Well, you know, you got to have some commonality. You probably all have to have OpenFlow running. You probably all have to have a certain willingness to collaborate with each other, to trust one another well enough to actually provide that level of service, etc. It's got to be some understanding about local control, and that you have the ability to pull this stuff out if it turns out that it is creating a problem. I mean, one of the things you really want to be able to do is protect your network against, you know, protect your production environment against the vagaries of experimental control. And so, you know, you need to have fast backout if you really need it. The real goal here is, you use the words illusion. I'm not, it may be an illusion, I'm not sure. You want to basically give an organization the ability to make it look like their network spans all of this environment. So what you're really doing here is you're not actually prototyping a multi-domain layer 2 service. What you're really doing is prototyping, expanding your layer 2 service across multi-domains so it ends up looking like a single domain service that crosses multiple boundaries. And so you don't any longer have the issues around how are you going to exchange content between multiple domains, because you've effectively made it a single domain for at least that virtual slice. So what do I mean by all this? Well, so you've got a switch. I mean, imagine that's man LAN, okay? A switch that I run. So I could put this whole, you know, stack of stuff on top of man LAN and operate it as an OpenFlow enabled switch with flow space firewall sitting there and so forth. And then I might decide to do the same thing in a second switch, maybe the Wix switch in Washington or in McLean. And I might talk Julio or someone into doing it into a third one. He already has, so I don't have to talk him into it. And so now you've got these 3 exchange points that are effectively operating this set of tools, okay? So that's all nice, that's great, you know, that maybe it helps them control stuff in the switch or not. I mean, maybe it, you know, technically it's a good plan just as an operator, you know, it doesn't really matter. You can tie these together, and actually this is a little bit premature because initially, of course, you'd tie them together with NSI just sitting off the, you know, just sitting off the switch directly off the hardware level. But you could also, you know, you could use NSI to interconnect these environments and use that as the tool to build circuits across domains and so forth. And you know, truth be told, that would work just fine. But you could also imagine doing something like this. You could say, well, you know, let's sit down and talk about this. We want to actually run, say we want to run Atlantic Wave, okay? Something Julio's been calling me on the phone about and saying you need to have a meeting with me, and I keep ignoring him about it. So I'll talk about it now. So imagine you wanted to run Atlantic Wave this way. So you could say, okay, let's create a virtual switch in each of these instances of flow space firewall. And let's put up a controller, we'll call it the A-Wave controller or something. And now that now controls a certain set of resources in each of these physical switches. And so you don't now have to talk to ManLAN, Wix, and AMPath in order to get a switch built. You just go to the A-Wave controller and you tell the switches, build me a path. And it does. So you've essentially flattened this whole thing out from 3 domains down to 1 domain. I mean, you could do that. In fact, we've sort of played around with doing that, and we should play around with it a little bit more. It doesn't even matter if these are individual switches, right? This can be a whole network. This could be the Internet 2 network, or this could be the AmLight network, or whatever instance of a network you wanted to think about with multiple switches in it, and then some others. And you could expand this out across whatever extent you're comfortable with in terms of being able to manage that many switches and so forth. And in fact, this is sort of what the Genie controller does for us right now. They have, that's what they're doing in their slice of our network, essentially. You could also, let me think about this one a minute. I don't remember what that one's for. Yeah, okay. You could also now not think about this as just crossing exchange point boundaries, but expanding networks into other environments. Okay, so now you've got your A-wave little instance going there that just connects up those exchange points and allows you to get paths going between Miami and New York very, very efficiently if you want to. But now you could also say, well, you know what? We can make another set of virtual switches here if we wanted, and we can put another controller up. I mean, I use OESS as the instance of a controller. It doesn't need to be OESS, obviously. It's just one that's easy to write in boxes, for one thing. And that could turn out to, for instance, be a NordGNet, right? NordGNet could work with us. They could expand into a set of places within the Internet 2 network that were of interest to them for whatever reasons. I don't know what they might be. And now they don't now even have to think about traversing mainland, right? Because while their traffic would go through there, they're not really traversing mainland. They're utilizing their slice of that switch, which now looks like a piece of their network. And these little green boxes all look to them like they are actually pieces of their network. So what you've done again is you've taken this whole complex set of switches that are interconnected and have different administrative controls, and et cetera, and you've flattened it out and made it look like a single thing. 2, 3, okay, well, we'll talk fast. So let's, anyway, that's sort of the conception, a conceptual thing you could do. And to some extent, we've experimented with a little bit of that, and we'll continue to do so. As I said, we've also gotten an implementation of ONOS done. So ONOS is something that we've worked with ON Labs to develop, or they did a lot of the developments. We're helping them deploy it. They have a service called SDNIP. So, you know, as long as I've been doing this stuff with Internet 2, which is longer than I might imagine sometimes, there's always been this sort of little fringe group that's been sitting there going, why do you need routers? We could, you know, just build a layer 2 network and put a route server up, and don't put these big, huge, expensive routers out there anymore. They're just a waste of money. The interfaces are horribly expensive. We can do this some other way. So what these folks at ON Lab have done is created an SDN-based or an OpenFlow-based tool that, in fact, does that to some significant degree. So the initial effort of the initial prototype that is utilizing the ONOS slice is some folks at Clemson, Duke, Florida International, Indiana Gigapop, Indiana Internet 2, the MAX facility at Maryland, and the University of Utah. They've all deployed some sort of a small routing engine. Doesn't have to be any big deal. It doesn't even have to be a real router. It could just be instance of Quagga or something. And a perf sonar node. We've deployed this slice. They've connected up to it. Initially, we're doing this with private ASs and private IPs, just because that would seem like one, it was just simpler to organize that way in terms of figuring out whose addresses you were using and so forth. But we will quickly be transitioning it into using public IPs and eventually running real traffic on it. And I'm just going to skip this and go to the interesting parts here. So this is what it looks like essentially. There's a small box hanging off the Salt Lake City switch. There's a number of them clustered around down in the southeast among different switches down there, Jacksonville, and a couple of them hanging off Atlanta, a couple hanging off Washington, one hanging off Chicago, and I'm not sure where the Internet 2 one is. And then there's these ONOS boxes up here, and they basically, and then there's this actually is also implemented at this point. This is the whole South American version of it. So basically what happens here is that you have these little routing boxes sitting off over here, right? And they basically inject routes that go up to the BGP speakers up there, right? So, I mean, you have to do BGP, right? You can't get away from that. But then what ONOS does basically is it takes that BGP information and it converts it into layer 2 and puts in rule sets to move the traffic so that the routers are never involved in the actual passage of traffic. Okay, everything that moves from that per sonar box, for instance, to the one on the top, happens inside the layer 2 network, inside the slice, without ever having to reference out to the routers. As soon as the environment figures out, this is what they want to do, they build the path, and then the traffic goes that way. Just kind of a very high level and no doubt lacking in detail description of it, but that's essentially what's happening here. And essentially what you've been able to do then is create an environment that doesn't have routers but has routing. Now you still, you're kind of saying, you still have some BGP speakers around the edges because you have to do that, but that's about all. And this actually is interconnected at this point to a European instance of this, as well as the US instance, and it's connected to the South American instance that I showed before. So we actually have this running between, Europe, US, South America, and every indication I've seen in the notes and such is that it works, that it's working just fine. And we will be continuing to work with these folks to develop this, to understand how it can be improved and enhanced and so forth. And no doubt there will be a goodly number of reports and discussions about it at future events. So I'm done.
Thank you for the presentation. Any question from the audience?
Hopefully I can answer them.
Thank you. So it was nice to see routing without routers. But the question is, how reliable do you consider this communication between the switches and BGP speakers? So basically it's SDN controllers, essentially. It has to be to have this network operational, because if you have a routing protocol on top of this, in the same box, right? So if some part of the network fails or you don't access some POP or whatever, you don't lose the routing functionality.
Yeah, I'm going to have a little hard time with that because, quite honestly, I'm not that familiar with how the internals of SDN IP work. But you're absolutely right. I mean, if any of the route announcements from the BGP speakers fail at any point, obviously you're not any longer going to be able to run traffic into that environment. So in fact, I believe they're doing this with multiple backbone devices, redundant servers, and they're trying to get to the point where that, that whole ONOS infrastructure is as redundant as it can be made to be. And, you know, presumably if you were doing this in a production environment, you would not be doing it with a single link, you know, coming across like this, right? You're going to have multiple links into the environment. You're going to be doing multiple announcements in order to make sure that the information is there and so forth. And you know, doing the same normal things that you would do to try to create any kind of a production environment, is my understanding. As I said, I'm sure you're going to see a lot more detail about how the ONOS activities develop as they have more experience with the test bed and more time to kind of internalize what's going on and report it back.
Okay. Maybe the last question.
I have a question to personal. So is there also an idea about what is the architecture, the performance measurement architecture for such kind of...
For this?
Yes.
Oh, well, right now, I mean, basically all they're using the persona boxes for is just traffic generators, essentially, just to, you know, to get some, to have something out there that you can verify, yeah, in fact, you know, this, traffic is going from A to B and so forth and so on. Ultimately, again, if this becomes more of a real environment, a production environment, then you would start doing persona meshes and dashboards and, you know, all that kind of stuff to verify where, you know, that all the links are still available and checking latencies and that sort of thing.
A small additional question to this: what is your performance verification of what you have mentioned?
I don't actually know the answer to that right now. Quite honestly, I haven't had a conversation with the ONO or the ON Lab guys about exactly what they're doing to verify. Yeah, you know, honestly, I think right now they're not very worried about performance. They're really worried about, does it work? And once you get past the, yes, we have in fact gotten reliable connectivity, we understand what we have to do to get new sites hooked up and so forth, and yes, we can start transitioning this into using real, you know, real production traffic, then they'll start being, I think, a lot more detailed about how they're going to do performance verifications and so forth.
I recommend you to keep in contact and discuss in detail what was the real usage. Thank you very much for all our presenters, all three presenters for the nice presentation. And a couple of reminders. Please visit the poster presentations and demonstration and give your evaluation feedback. And now the lunch. Thank you very much.